In the summer of 2011, paleontologist and science writer Riley Black was on a mission. Walking through the Montana desert, she was on the lookout for a Tyrannosaurus rex.
The field team that I was with, they had found a couple Tyrannosaurus rex bones in this particular area, and they wanted to see if there was more. Usually when we find a dinosaur, a big fossil, it's really a multi-year process of even locating where all the pieces are, much less getting them out.
But that day, she wasn't having any luck. Sitting atop a rock, she pulled out a geological hammer, sometimes called a rock pick, to dislodge a little piece and try to discern its composition.
When I did that, there was a leaf on it. And for a second, I thought that this was a leaf that had maybe been washed or blown between the rock layers. This happens all the time. Debris kind of gathers. But when I went to touch it, there was no sort of recognizable leaf surface. And there were certainly no trees that I could see in the vicinity that could have left leaves like this behind.
She quickly realized it was a fossil, and it turned out there were a bunch of them, preserved so perfectly that you could see the individual veins of the leaf.
It made me think of picking up a maple leaf when I was a kid, and you see all those intricate little veins. You can hold it up to the sunlight. In this case, it's rock, so I couldn't do that part. But it still just fascinated me that here's this gorgeous fossil, something that feels like it shouldn't be preserved in a way, something that's so delicate and relatively ephemeral. And there it was.
So although Riley was on the hunt for a T-Rex, finding these fossilized leaves likely provided so much more information than if she had come across the dinosaur's fossils.
It really struck me how much it's easy to overlook a leaf or a fossil plant as something that seems plainer. But without plants like that, you would not have big herbivorous dinosaurs that needed to eat a whole lot of plants to grow to the size that they do. And without those herbivorous dinosaurs, you wouldn't have the carnivores. All these things are really intertwined and interrelated.
And now in her book, When the Earth Was Green, Riley is unpacking that idea. From oxygenation events billions of years ago, all the way up to the last ice age. Welcome to Tiny Matters, a science podcast about the little things that have a big impact on our society, past and present. I'm Sam Jones, and I'm joined by my co-host, Deboki Chakravarti. And you could probably tell by the intro, but we have a really fun episode for you today.
And it's about plants.
Yes.
We've had a bunch of listeners asking for more plant episodes, and, we like to make our listeners happy.
We do.
So today, Riley is going to help guide us through a few pivotal moments across the history of our planet, chronologically laying out the back and forth between plants and animals through climate shifts and apocalyptic extinctions, and how that's led to the world we live in today. We'll begin around 450 million years ago. Plenty is already happening in the ocean with early plants and animals, but now plants have begun to make their way to land. And if you're picturing a typical plant from today, that's not it. We're talking about liverworts, likely the earliest land plants.
Liverworts are small, green, spore-producing plants that live low to the ground and seek out moisture. Plants moving onto land had more impacts than we know. But for this little snapshot in time, we'll talk about their impact on bony fish called sarcopterygians, who we actually share a common ancestor with. Their bodies were the early blueprint for our bodies today.
They had these chunky, very block-like bones. Those were still the precursors of what our arms and legs are, the legs and appendages of a deer, a cat, any vertebrate with limbs that you think of. These sort of precursors way back when animal life was still entirely confined to the ocean pretty much.
And we can thank liverworts for aiding in the development of those blocky bones because they helped mobilize calcium. They extracted it from the rocks and soils in which they grew. Then, when they would die and decompose and it would rain, the calcium would make its way into the ocean and help these animals build much stronger bones.
So there's this whole chemical process that's going on the shoreline that's mobilizing a lot of minerals that previously were just kind of bound up in rock. And calcium is part of that And that's what critters in the ocean are using, not just to build their shells, but also bones inside their skeletons. That we don't see sort of this diversification of critters with different forms of bony skeletons until we have this kind of infusion of the relevant elements into the seas. So even though it might seem entirely unrelated to the trees and plants we see around us today, the fact that our ancient ancestors were able to build their skeletons out of some of these essential elements is largely thanks to what plants were doing on land already.
I just didn't think a lot about availability of certain elements so that you can actually do things like build a skeleton. Because if you don't have those, it would have completely altered the evolution of a lot of animals. I was just so struck by that.
I mean, we often don't think about the prehistoric past in that way, right? It's often like what lived when, who was related to whom, who was eating whom. But the forms that organisms take and why they're in that particular shape, it often gets thought of in terms of like function, right? Like what is the animal doing, but not in terms of availability of certain resources.
Okay, so let's move up in time a bit, relatively speaking, of course, to around 300 million years ago. This is a time when Earth's ecosystem is rapidly transforming.
If you look at deep time, the number of ice ages and hothouse periods and all these things going back and forth and how they're influenced by living things, the climate is not something that just happens. It's something that's very much influenced by the things living on the planet, and plants have had a huge role in this. Around 300 million years ago or so, you have plants that are really taking hold, really for the first time on land, growing not just kind of as like scum on the shore, but moving further and further inland.
And as plants expanded in number and range, they increased the concentration of oxygen in the atmosphere. During photosynthesis, plants convert carbon dioxide and water into oxygen and the carbon-rich sugar glucose. With carbon now trapped in glucose, that leaves oxygen to be released back into the atmosphere. During this time, about 35% of the atmosphere is composed of oxygen. For comparison, our atmosphere today contains about 21% oxygen.
And prior to these levels, more than a billion years ago, things like fires basically would not spontaneously happen on the planet. Oxygen levels were too low. So it's kind of ironic, especially, considering what's going on in Southern California as we record this, a lot of the fires and stuff that we see and contend with now. In the ancient Earth prior to 300 million years ago or so, those sorts of things would not have been possible, not just because there weren't, forests yet to have these fires in, but just there wasn't enough oxygen in the atmosphere to allow them. So the fact that over time plants have evolved things like fire cycles is adapting to the world that they created just by existing.
As a side note, there are some plant species that require wildfires to propagate. For example, the scrub oak needs fire for its seeds to germinate, and some tree cones won't open and release their seeds without fire. That's neither here nor there, but it's just really incredible what plants have done, not just in the context of their impact on animal life, but in terms of their own adaptations. Because, incorporating fire into your life cycle is pretty extreme.
Now let's fast forward again to around 60 million years ago. This is 6 million years after the asteroid impact at the end of the Cretaceous period that killed off the non-avian dinosaurs. Earth's first tropical rainforests are beginning to spring up, allowing for a giant, and most, including I think Taboki would say terrifying,
Absolutely,
creature to thrive, the Titanoboa. The Titanoboa is the contender for the largest snake ever. Based on fossils recovered in the early 2000s in Colombia, the Titanoboa could have been up to 47 feet long and weighed 2,500 pounds. Okay, so let's get back to Earth 60 million years ago. It was what you would call a hothouse planet.
Basically, CO2 levels are elevated. You had some changes to weather patterns and where rain was falling. And in the ancient tropics, what's now Colombia, you had these really thick, dense rainforests where you had Titanoboa, this enormous snake, a number of crocodiles, but also mammals. There are cocoa plants, and there are peppers, and there are palms, and all these different forms that you can still see in tropical forests in the modern world.
Those lush tropical rainforests just weren't possible in the days of the Triceratops and Tyrannosaurus for a couple of reasons.
One is that the average size of a dinosaur at the end of the Cretaceous was a multi-ton animal. This is something that's wandering around. It's trampling plants as it moves. It's eating plants. It's spreading seeds through what it eats and leaving dung behind. And forests would be relatively open. You'd have all these basically dinosaur-sized holes in your forest, one way or the other. After the non-avian dinosaurs went extinct because of the asteroid impact, there are no really big animals anymore. Almost everything that survives, at least on land, is about the size of a house cat or smaller. In water, you still have crocs and things like that that can get big. But on land, plants can really get a jump on growth and start building forests in different ways. And even the construction of what those forests look like.
Before the Cretaceous extinction event 66 million years ago, gymnosperms, which are plants that have their seeds exposed as opposed to, say, enclosed in fruits, those were the most common plants you'd find in forests. These include conifers similar to the pine, spruce, and monkey puzzle trees we see today. Which, side note, if you don't know what a monkey puzzle tree is, look it up. It's really cool.
It is.
And during the Cretaceous period, about 125 million years ago, you had what's called the Cretaceous resinous interval, a period of mass resin production from these trees.
When they're damaged, they exude resin, and that resin will get stuff stuck in it as it gums up the tree. And if it falls to the ground and gets covered up, you get fossils and amber. And it was this time period that lasted, about 20 or 30 million years, where just these resin-producing trees were everywhere. If you find fossil amber, it's probably from this time period.
That's pretty cool. I had no idea that so much resin was being produced back then, and that amber is just fossilized tree resin. Props to Jurassic Park for accurately capitalizing on that being the vehicle for preserving dino DNA. Not going to say that the rest of the science checks out, but that was good. All right, so to get back on track and back to 60 million years ago, after the extinction of the non-avian dinosaurs, there's a major shift in plant life. Instead of these gymnosperms, flowering plants called angiosperms began to take off.
So you have this major shakeup of life. There is a mass extinction of plants. The survivors tend to favor angiosperms, and they're growing really close together. And there's a chemical component to this as well, that the asteroid impact, the asteroid itself, 6-mile wide chunk of rock, was a carbonaceous chondrite. It's a kind of asteroid that has a lot of iron in it. So basically when it was pulverized and all those bits were sent all over the planet, either as dust or as little bits of rocky debris, you have this infusion of iron into the soil that's really good for the angiosperms. So you basically had this fertilization of the soil following the mass extinction that really gave a boost to plant evolution.
With all of these changes combined, a closed canopy forest emerged, a lot like our modern rainforests, the perfect environment for an ambush predator like Titanoboa to slink over muddy embankments and glide across pools of water. The now extinct dinosaurs would probably not have done so well on that terrain, despite what some popular movies might want you to believe.
Whenever you see a movie with dinosaurs in it, like Jurassic Park or a lot of old art and stuff, they'd be living in these very dense, kind of sweltering forests, and they would have absolutely hated it. They would have made all these dinosaur-sized gaps in it. So the environment that I feel like, at least in a pop culture sense, that we most associate with dinosaurs was not actually possible until all the big ones went extinct.
Yeah, as I was reading the book, I was thinking back on how many drawings or paintings or movies are showing these big, lush rainforests with T-Rex walking through them, which would not have been the case. I'm sure every movie that you watch where there's some dinosaur element, you're like, that's not right, that's not right, that's not right.
Yeah, I mean, we all have our preferences about dinosaurs, but we're still waiting on one that I think puts dinosaurs in their real setting. It's hard sometimes to imagine, the world that they're in, how different it was from ours.
So now going forward many millions of years to something that in the span of time just happened yesterday, the chapter that you have after the ice that looks at around 15,000 years ago, you talk about, is it mammoth?
Yes, the American mastodon, Mammut americanum.
Yes. And so I'm wondering how these animals were also shaped by their environment after Earth started to really thaw out. What's interesting is I think they had been around for almost 4 million-ish years at that point, and they were going to go extinct not too long after. But yeah, I'm kind of curious, coming out of an ice age, how did the plant life impact their lifestyle and survival?
So the American mastodon is always a bit of a heartbreaker for me because it feels like they should still be here. When we think of the big elephants of the ice age, you have mammoths and mastodons for the most part. And I think in popular culture and depictions, we often put them together, that the Ice Age is kind of monolithic. That's like it's literally everything was covered in ice, and that's how it was until it melted. But the fact is that there were interglacial periods, that you basically had the waxing and waning of glaciers.
So when the glaciers expanded, the earth was cooler and drier and favored grasslands. There were still some trees, but things were a lot more open. And the woolly mammoth thrived, grazing on grasses and leaves and bark from willow trees, using their flat molars to grind them down. But when the glaciers would recede and things would warm up and get a bit wetter, the mastodon was happiest.
That's when you'd see a lot more mastodons wandering around. And they were shaped a little bit differently. They'd been around for, as you said, about 4 million years by the end of the Ice Age. And they had these bumpy teeth that were really, really good for breaking down branches and things like that. So they were basically forest elephants, that they liked woodlands, that they liked kind of swampy, bog-type habitats.
Mastodons would travel as far south as Florida, where they would eat melons and Osage oranges. And let's just say there's evidence that they were definitely eating, enough to warm up our atmosphere. Because as they were eating all of this plant material, their intestines were fermenting it, and the resulting gas needed to go somewhere.
There's a bit in the book where basically I talk about mastodon farts, which seems like an odd thing to end, a science book with. They end up releasing a lot of methane. And paleontologists have actually been able to track this, that there was sort of a methane drop with the extinction of a lot of megafauna, not just mastodons, but giant ground sloths and other large creatures, basically billowing out all this extra methane and greenhouse gas into the atmosphere. So it was not determining the course of the ice ages by any means, but certainly influencing what the global climate was. So all of these systems kind of feed back into each other, where the climate influences where the glaciers go, which influences the landscape, which influences what the animals are eating, and then they in turn influence the climate once again.
I think there's this big conversation right now about gas, mainly cows, I think, that are the biggest issue with methane release. But you don't think about it that far back, but these are massive animals. These are really massive animals. And so, of course, that's also going to have an influence.
Absolutely. These animals were not just so much bigger than many of the animals that we see around us today, but so much more numerous that we are living in a time that I think of as a megafaunal lull, in that most large animals that remain, many of which are Ice Age survivors, are not as widespread as they used to be. It wasn't just that animals were bigger, but there were a lot more of them. There were a lot more species of them living side by side, that you'd have these complex communities. So like I'm living in Salt Lake City in Utah. Around this time period that I'm writing about in the book, there were mastodons and mammoths and giant camels and saber-toothed cats and dire wolves and the American lion. It wasn't just like you had one big herbivore and one big carnivore and that was kind of it. You had these communities of so many different creatures that are all shaping the landscape by what they do and their interactions with each other. We see this even with modern day wolves, this sort of idea of predators creating a landscape of fear. So herbivores know where they're vulnerable, so they'll feed in certain places and not others. And that affects how plants grow and what the ecology looks like.
Riley told us that while she was writing, she was struck by how plants underwrite so much of our existence. Not just the food we eat or the air that we breathe, but even what our anatomy looks like.
We are the descendants of prehistoric apes that lived in the trees. The fact that we have so much arm flexibility, whether that's swinging a hammer or throwing a softball or whatever it is, it's directly attributable to the fact that our ancestors pre-Lucy, pre-Australopithecus, were basically clambering around through tree branches, and they needed that flexibility. And as forests started to recede about 20 million years ago, and you'd have the spread of grasslands, ancient primates basically had the choice. Do you stay connected to the forest, or do you start to venture out further and further? And our ancestors went with the terrestrial route. But we still, especially in our upper body, bear so many hallmarks of creatures that lived in the forest. Even the fact that we have binocular vision, that we can stare straight ahead. We have grasping hands with thumbs. That goes back even earlier to some of the first primates that lived in those ancient forests shortly after Titanoboa was around. So many things that I think we just kind of take for granted or take as it is. If you think about, well, what do plants have to do with us? It's usually quite a bit. It's usually there's some ancient moment, this ancient adaptation or kind of interaction that sets up so many further changes. And if the timing was different or those interactions were different, life would probably look very different today.
We are, of course, in a moment right now where the climate is rapidly changing, and every year more species of plants and animals are going extinct. Given how much time Riley spent thinking about climate events and devastating extinctions, I asked what she thinks about our current situation and if there are any connections to the past.
Something similar to our present moment naturally happened in the ancient past, something called the Paleocene-Eocene thermal maximum about 55 million years ago or so. And this is when there's this vast infusion of greenhouse gases into the atmosphere from different planetary sources, but things changed relatively quickly. The planet got quite a bit drier. You see some large animals becoming smaller, which is relatively common when things heat up, where rainfall changed and ocean currents altered. These are the sorts of consequences that we can expect to happen, that it's not just a matter of getting hotter, but where things live. And even things like ocean currents, which we just kind of assume that they're going to do what they do in perpetuity, can reverse themselves or fundamentally change, which affects some other part of the ancient planet, which creates this sort of domino effect. And I think we don't have a crystal ball to know exactly what's going to happen. But I think what I take from all of it is that, when we look at these ancient events in the past, especially things like mass extinctions or these relatively rapid changes, those were things that just happen as a part of Earth's processes. And they're painful to life in many ways. Life survived and certainly thrived afterwards, but there were extinctions. They were catastrophes in their own right. And now we have the choice to do something different. We do not have to say, well, we're the asteroid on a collision course and there's nothing we can do about it. Whatever small thing that we can do, especially specifically talking about climate change, the less carbon dioxide and methane that we're putting out into the atmosphere, the better. Even if it feels like the most minuscule amount, it is something. And I think that's really what my hope for this book is that I don't really care if people remember specific figures or organisms. I want it to change the way that they see the world around them, and to look at plants or to look at animals that eat or interact with plants and think about those relationships, how they formed and have been maintained or shifted over vast amounts of time, and how are we now affecting those changes? Are we going to create a planet that's more of a garden? Are we going to be good gardeners and think about the consequences of what we do? Or are we going to pretend that it's kind of inevitable? The more that we know and the more that we understand, the more that we act with intent, we can maybe forestall some of the catastrophic effects that we've seen before in the fossil record.
Let's tiny show and tell.
So, Sam, I don't know how you feel about beer, but I really love sour beer.
Me too. It's I would say of all the beers that I could choose from, I always go sour.
It's like I either do sour or dark. It's like kind of the two extremes, but like those are my go-tos. And I didn't know this, but sour beers are apparently really tough to make. It's a really time-consuming process. Some of the steps can take a really long time. Fermentation can take months or even years. And because of how long some of these steps are, there's just a lot of things that can go wrong, I guess, along the way. Like you don't always know what compounds are going to show up. And obviously that's going to then affect the flavor of the beer going forward. So these researchers in Norway, they wanted to see if they could reduce the number of steps in the overall process, and they turned to an ingredient that was surprising, at least to me. I'm curious if you have any guesses about what it could be.
A surprising ingredient, specifically to sour beer.
Yeah.
Jolly Ranchers? No.
That is a great guess, but it's actually peas.
What?
Yeah.
Really?
Yeah, because apparently peas make this specific kind of sugar that doesn't get consumed by the yeast in the beer, but it will get consumed by the brewing bacteria. And so that's you need the specific kind of sugar to make that happen. And they took the sugar from field peas and they used it to make different batches of sour beer with different bacteria. And they were able to ferment it for just 19 days. And then they did some chemical analysis to see what kind of things were showing up, and they also gave samples to taste testers. And they found that even with the shortened brewing time, all of that pea sugar got eaten up, and the flavor was also apparently pretty good. There was good fruitiness and acidity, and importantly, there were no beany flavors. Apparently when you make things with peas, it can sometimes taste like beans.
Yeah.
So I was very amused that peas were the secret ingredient.
That is so interesting.
Yeah.
Wow, that's really cool. I'm going to think about that next time I have a sour beer.
Right.
Okay, so we do not have the same tiny show and tell. It is confirmed. because I'm going to talk to you about whales.
Yeah.
All right, Deboki. So we all know that whales produce sound.
Mm-hmm.
It's how they communicate. They sing to each other. Essentially, there's this whole underwater world of language.
Right.
Baleen whales, whales that have baleen, which are these like fringed plates of keratin in their mouths that allow them to sieve their plankton food from the water.
Mm-hmm.
They are more solitary than toothed whales. And they seem to face a lot of predatory attacks from killer whales, especially mother-calf pairs. What I didn't know is that the killer whale is the only natural predator of baleen whales.
Oh, I guess that makes sense.
Kind of makes sense, but in my mind, I'm like, how do you only have one predator? But I
Yeah.
mean, we're really messing stuff up too,
Right.
obviously. But natural predator,
Right.
killer whales. So when attacked, there are some species of baleen whales that will fight back,
Mhm.
but others will choose flight.
Okay.
Like they will try and get away
Got it.
as best they can. So keep that in mind,
Right.
because there's new research that shows that some baleen whale species will call at such deep frequencies that they're completely undetectable by killer whales, which can't hear sounds below 100 hertz. And these tend to be the whale species that will flee in the face of attack. And that includes blue whales, fin whales, minke whales, a couple others.
Uh-huh.
But the higher frequency singing baleen whales generally seem to fight back when they're attacked. And those include the right whale, the bowhead whale, the gray whale, and the humpback whale. These whales also tend to be slower moving
Mm-hmm.
and more maneuverable, is how they explain it. But essentially, I think like if you're slower,
Yeah.
you kind of got to fight.
Right. Yeah.
Right?
Yeah.
So what these flight baleen whales, I will call them,
Yeah.
are doing is likely something called acoustic crypsis, which I just love that
Yeah.
name, where whales will call
Mhm.
at such deep frequencies where they're acoustically invisible to
Uh-huh.
the killer whales. So it makes it so much easier for them, A, not be detected,
Yeah.
but then also get away.
Right.
If a lot of them are just not detecting, like
Yeah.
they're sending out calls to each other to let them know, hey, we're in danger. But the killer whales are like not hearing anything.
Right.
And so, yeah, like researchers think that this could be a really cool, important defense mechanism adaptation that helps these baleen whales that don't fight back, that need to get out of there to survive.
Thanks for tuning in to this week's episode of Tiny Matters, a podcast brought to you by the American Chemical Society and produced by Multitude. This week's script was written by Sam, who is also our executive producer, and edited by me and by Michael David. It was fact-checked by Michelle Boucher. The Tiny Matters theme and episode sound design is by Michael Simonelli and the Charts and Leisure team.
Thanks so much to Riley Black for joining us. We've left a link to her book, When the Earth Was Green, in this episode's description. We'll see you next time.